UNLV. Daniel is a professor at UNLV. Has been there for many years. Before that, he got his PhD from the Copernicus Institute in Warsaw, right? And he did postdocs, including postdocs at Boulder, University of Colorado at Boulder, and Princeton University. And he's done a lot of work on accretion and outflows and feedback from accretion. And so he's in particular done a lot of work on a lot of numerical analysis on that. And I think that's what he's going to talk to us about today. Thank you.
Thank you very much, James. It's a pleasure to be here. Title is slightly different than the one I submitted, but it's more or less the same subject. There are just many ways of saying the same thing. The list of collaborators is quite long, and it includes Shane, and I hope I will have time to show you some preliminary results from a project that he and Jack, who visited you a couple of weeks ago, and James and myself are involved. I will focus today on telling you about the results from numerical simulations carried out by my former two postdocs, Monika Mości-Brodzka and Paramita Barai. It all is connected also with the work of other former postdocs of mine, Ruichi Kurosawa. So my motivation to this is not really about energy and feedback and galaxy evolution, but rather from understanding the astrophysics of supermassive black holes. So we know of supermassive black holes in galaxies very far away through the enormous amount of radiation which is emitted by objects that we call quasars. So those systems have so-called broad line regions and narrow line regions. So these are regions which we believe are responsible for production of very broad emission lines of ionized metals, but also gamma lines. So the width of these lines is so high that it cannot be thermocoupled. It is related to large-scale outflow, most likely. It's not turbulence because that would be supersonic. So these are hallmarks of those systems, but we don't know actually the geometry, the dynamics. People talk about the existence of clouds in those regions, but we don't know how those clouds are formed, how long they survive. They likely not survive for a very long time. So you may look at this literature and see that not many people work on these subjects anymore, but please do not be mistaken. This is not because the problems have been solved. It's just a higher. But understanding those regions is very important because reverberation mapping, which relies on measuring line widths and velocity dispersions, requires some knowledge about broadband regions, which is needed to determine the mass of the black hole. Since those regions are much further away than the most luminous parts of the accretion disks, they are probably places from where the matter comes into a black hole. So understanding how the matter flows through narrow line region and broad line region and getting to the black hole is important to know what is the accretion rate, why is it so high, can it be higher, can it be lower, why systems are of different luminosity, spectral energy shapes, and so on and so forth. And finally, just to be connected with the rest of the astrophysical community, because those sources are so luminous, they probably affect the things around them. And if so, we want to understand how. So this is a cartoon version of AGN feedback and cycles in elliptical giant galaxies from paper by Lukacs and Jerry Osrak and myself. So galaxies are big, lots of things are going on. You have supernovae, you have star formation, you have AGN, and they are somehow connected. And we want to understand what regulates star formation, how do you prevent galaxies from being not too massive, not too bright. As Sean knows, I am not an expert on most of it. I work mostly on that part, so I will not pretend that there will be something new and exciting about those parts. you have to go to general look. So my talk would be mostly about the innermost parts. Okay, so AGN feedback, few remarks of mine. People who do galaxy formation talk about AGN feedback because they are talking about beat systems and processes on very different scales. They cannot model things directly. So they refer to something like subgrid physics, meaning that they try to use understanding of what's going on small scales and implement this on scales that they close to not resolve. We do it all the time. When we are talking about thermodynamics, we are not determining velocities and position of the individual electrons or ions. So from that point of view, this is subgrid physics, which is well understood. So this is important to do that. And we know how to control systems, how to connect things. This is the success of the steam or industrial revolution, right? We put devices that control the amount of steam and pressure that is powering choo-choo trains and water pumps and things like that. So this works on the centrifugal device works this way, that those weights spin depending on the amount of steam that is released. The faster they spin, the centrifugal force makes them to move away from the rotational axis, and that opens the valve that allows the extra steam to escape so that the engine does not blow. Okay? So we need to be aware that some people actually do not use subgrid physics, but do subgrid engineering. They know what they want, and they sometimes just put what they want. They would try to justify that it's physical, but you have to be careful about it.
You know this talk's being recorded, right?
I gave that part on more than one occasion, and I'm still surviving. So let me give you an example. Okay, you can use your favorite computer program to express this feedback. That if you know the accretion rate at large radii, you can assume that it's a black hole accretion rate, and then you can put it to this equation and get the luminosity of the black hole. Okay, so you use this with that, and then you put it back here. Okay, but this is a very simple prescription, and sometimes it does not do what is required. For example, preventing system from being super heavy. That's why you get this. Prescriptions like that do not physically control the maximum accretion rate. They basically use Fortran statement, if this number is larger than I think, then keep it small. So we would like to have a physical model where these things do not happen if this is true, instead of basically implementing our understanding of what's going on small scales. So I will give you examples of a few numerical simulations that address some of the issues of inner working of AGN. So this would be, in most part, results from multi-dimensional time-dependent simulations of accretion discrete. So this is basically what is the physics of subgrid. We would like to forget about the rest of the galaxy and make global but not so large-scale simulations and understand what happens with the gas which is available for accretion, how much it reaches the black hole, how much is being expelled, at what rate, with what energy. And then we'll try to be a bit more ambitious and talk about large-scale outflows and inflows to see, can we model AGN feedback directly, and to what extent? Can we attack the problem directly and put everything, for imagining that you have, you can afford very high resolution, that you have a huge computer and you can put everything and you don't need to do any subgrid. So I'm coming to this from cataclysmic planet fields. So let me talk about accretion disk means. So this is old stuff that I've done a decade ago, but I will tell you what is the latest in our understanding of broad line regions, broad absorption and emission line. Okay. So you basically can attack this problem directly. You use spherical polar coordinate system. You assume something about this, which is over here. What is the density distribution and temperature and radiation field? You may put in radiation from the center, and you try to calculate the structure of the outflow that will emerge from the surface. So you are solving the equations of hydrodynamics, and what you want to do is to add radiation pressure. And in systems like quasars and cataclysmic variables, a fair amount of total luminosity is in ultraviolet, which is important because when the gas is ionized by ultraviolet, the opacity of the gas is very high in spectral lines. So there is a very good coupling between radiation and gas. This coupling allows the radiation to share momentum with the gas and drive it out. So to estimate this force, you have to integrate in over entire disk surface, take into account ionization state, things like that, but that has been done. So what happens to the disk? Basically, it will be not a naked disk anymore. It will have an outflow that will look more or less like this, with the following properties: that as often terminal velocity of the wind is comparable to the escape velocity from where the wind was launched from. So if the wind was launched from very small radii, its velocity may be very high. So high that it's capable of explaining broad absorption lines in some quasars. Another feature of this outflow is that mass flux density is a strong function of radius. The wind loses more mass at smaller radii than a large radii. And the wind comes mostly from the part of the disk which is radiating in ultraviolet. Other parts which are cooler have not enough intensity, also not enough opacity to drive the wind. So you may be under the impression that there is a wind coming off from large radii, but it is actually the wind that is launched from here and spread over a large area of confused space. When you add radiation from the center, and especially X-ray radiation, soft X-ray, this wind will be changed because X-rays will ionize gas and it won't be able to couple with radiation as efficiently as it used to. So X-ray radiation, by ionizing and even fully ionizing, reduces the opacity, so the wind may not survive. And that is the so-called over-ionization problem that has two general solutions. Either you refer to the wind being clumpy and the gas protects itself from over-ionization by gaining clumps, or as suggested by Norman again almost 20 years ago now, the outer wind can be shielded by the inner, by some gas which is at small radii. He used the word hitchhiking gas. I think that most people these days call it a failed wind. But it's more or less the same thing, it's just a filter. So what will happen when you add radiation to the X-rays? What is the solution to the over-ionization problem when you try to attack the problem directly by numerical simulation? So what you do, you have this force, but now you add X-ray heating. That will change the ionization and will change the opacity here. So those equations will be coupled through the thermodynamics of the gas. The inner part, if exposed directly to the X-rays, will be ionized and it will not escape the system, but it will be still there. So what you will see is that the failed wind will work as a screen or a shield to the outer wind. So although the wind is weakened, collapsed in certain regions, it's still there, and it's still very strong and very fast. Okay. So this is 10 years old stuff, and I just, as a reminder, told you about it. What I would like to do next is talk about observational consequences of those solutions. Yes?
Can you remind me, what is the radial direction? What's the outer radius?
So this is 1500 black hole radii. So it occupies about 2 orders of magnitude in radius. The computational domain was chosen in such a way that it covers well the UV and EUV part of the standard circular simulating test. Yes.
It looked like the ring was sort of like pulsing.
Yes.
Is that?
I will show you a movie which will show demonstrate this pulsing in more detail. Okay. So my approach to study AGN feedback and things is that I want to have a physical model, say, for a given type of beams, but also I want to verify that what is being found in simulations is consistent with observations. So in collaboration with very many people who work very hard, we managed to compute spectra based on this calculation. So we can confirm that this not only makes sense, it's not only a plausible solution to physical equations, but also connects well with observations. Yes?
Quick question. Are you resolving the disk scale, or have you done some engineering on the launch of the material, or is that done self-consistently from the surface layers?
So the lower boundary conditions are chosen in such a way that the density is constant and it's fixed in time. I am not resolving the structure of the disk. Now, the question I often get is the solution dependent on the density which I keep constant? And the answer to that is that as long as this density is high enough, the solution is not dependent on the density. It is because the mass loss rate, which is most important in this context, is an eigenvalue equation and is determined by a critical point. So as long as the density is high enough that the gas is first subsonic, then supersonic, subcritical, and supercritical, the solution is independent on that density. Basically, the mass loss rate is determined at the conditions near the critical point, not at the basic rate. So this is a Cartesian version of the simulation.
Can I just ask one more?
Yes.
So most of the wind is coming from only a couple hundred gravitational radii in that radius.
Density.
10. Yeah, it's less than 100.
Yeah, basically where the UV peaks, so where the temperature of the disk is 50,000 K. So this is a movie which is showing exactly the same thing as before, but in the but as a function of radius in the radius and theta in the spherical polar coordinate system. And this is not radius, it's actually the grid point number in distance and in theta. So this is the disk. Okay, and this is the passing that you, I think, have in mind. So what happens here is that the reason for this unstable solution, time-dependent configuration, is the following. To launch a wind from a Keplerian disk, that's nothing. Because a Keplerian disk is, by definition, the place where all the forces balance each other. Gravity, in radial direction, gravity is balanced by centrifugal force, and there is no net force in the radial direction. So to launch something from there takes nothing, but to eject it takes energy and force, because as you go, for example, vertically up, gravity increases linearly with distance. So it gets harder and harder. So, and this gas is then exposed to the X-rays. So it is launched all right, but at some point, as it accelerates, density drops, it will be optically thin, and it will lose the support from the radiation, and it will start to fall. And these pulsations are basically manifestation of the fact that this gravitational force is not overcome by radiation pressure. And this thing creates the shield. This is the hitchhiking gas, or the shield, that provides the screen to the X-rays for the gas which is launched at larger radii. This gas here is behind this gas and can accelerate. Now, this gas is optically thin to X-rays, but it is optically thin to the UV photons which are emitted from here. So the fluid element at this location sees a lot of UV radiation coming from the disk which is underneath. Okay, so this pulsation is basically due to the fact that the wind does not reach the escape velocity. It's like from your ball out, it goes out, slows down, it comes back. And that keeps repeating over and over.
So I thought this was really amusing that you could see through it in the UV and not in the X-ray, because it was unexpected, right?
I was just puzzled about that.
Well, on the other hand, it's true of our atmosphere. Right? So, you know, I sure, when I realized this, it's like, when I thought of the atmosphere, I thought, okay, well, we're still placed.
So this is 2000, 2004 stuff. Since then, what I've done in this area, well, as I said, I was giving people who have photonization codes to calculate the spectra. And I also was involved in doing that. So when you take these structures, which will look like this in 3D, okay, you can calculate line profiles for a fiducial UV transition. And this line profile, the solid line is for pure absorption. The dashed one is when there's absorption and scattering pattern. This line profile, the strength, its shape, and width depends on the viewing angle. The same like in cataclysmic variables, where we know the inclination angle. So you have broad emission line, but as you go, so this is face on, but as you approach viewing the system almost edge on, you start to see P Cygni-like absorption line, where you have blue shifted absorption and line center emission line. So this is consistent with the observation. And then there's this issue, will you be able to produce single peak emission line instead of a double peak emission line expected from a Keplerian disk? And this is again something that Norm worked on, made a great contribution. You saw that the solutions are time dependent. So this is just line profile as a function of inclination angle for a given snapshot. So what I've been working on with others, I basically generated line profile for a given inclination angle as a function of time to connect this with observations. Now, this for me is a big test and a big challenge, because one of the criticisms for winds to be launched from smaller radii rather than large radii is that time variability. Quasars have been known for 50 years, and initially we had observation of the given quasar once, twice. But with time, people have monitoring campaigns, and they took spectra of line profiles more than once, and they didn't see much of the variability. However, within the last 5 years or so, we see that broad absorption lines in quasars will change in time. We have cases that broad absorption line disappears. Sometimes we have also cases where the absorption line appears. So it has been quasar without any absorption lines and that is. And also with I.o.s, the latest version of Sloan survey, Neil Brandt with his graduate students monitor, and they study what happens with the shape and the width of the profiles on different time scales on months, weeks duration. Another important thing, an implication of these results is that if the broad absorption lines are coming from a disk which is very inhomogeneous wind, determining from observation the mass loss rates is tricky. Most people use very symmetric models for that. They use some type of opening angle arguments to basically use the information that they can measure, which is velocity, and then to say what's the total mass rate. So this is just an illustration, is that covering factor. So the disk physically covers a good fraction of the entire disk. But from spectroscopical point of view, at the given frequency, the so-called resonance surface may cover much smaller area. And that fraction that the wind is covering can be very frequency dependent. So this is a map of a disk intensity corrected for the existence of the wind above it. And this is for different velocities, different wavelengths. So this is for the line center. This is some over here, and this is some over here. So people who do interpretation of line profiles have to be aware of those complications. Now, the shielding gas implies that to the observer, the broad absorption line quasar should be a weak source of X-rays. That's the consequence of the overall configuration of the outflow. And this is consistent. We know that most bulk quasars are X-ray. But we want to be more specific, so Nick Church, and please don't use extra organization code, and computed line profiles for different inclination angles. So you see that when you look through this region, the imprint of the loop from the spectrum is very weak. But when you look at much higher, you start to see absorption lines and then even higher inclination angles. So the spectra are very promising and provide support for this model. So with this optically thin in this zone, so that we won't be able to detect it, then it's Compton thick at very high inclination angles and produces most interesting spectra when you are looking at it within this inclination angle range, which is over here. So this is pure transmitted radiation. So we assume the power law X-ray spectrum and we computed photonization structure and absorption caused by this. But you can do better than that, and actually Stuart Sim he can use Monte Carlo techniques to calculate the wind structure and also calculate contribution to the radiation from scattered photons. And when he did that, he could compute the spectrum for different inclination angles. So what you see here is the net, direct, and scattered contribution to the spectrum. And he could calculate line profiles, and then for different inclination angles. Okay? And what he found is that when you allow for scattering, the shielding gas works less efficient than we originally thought. But it's actually very logical and should have been predicted. Meaning that those photons which are observed here can be scattered more than once, and they can reduce ionization state of the gas on this side. So it would be interesting, yet very challenging, to add photonization multiple scattering to hydrodynamical simulations to check that the shielding gas will play its role, even if we allow for scattered contribution of the radiation. So now we reach the point that we have a physical model for broadline regions. We find that they can move very fast, a good fraction of speed of light. They are carrying a lot of mass, half solar masses per year. And the same models do quite a good job in predicting spectral line features. So now we can say we have a physical model for the wind, and how we can use this information as subgrid physics. One of the way of doing it is just those calculations give you numbers like mass accretion rate / luminosity of the disk and the mass loss rate. So when you calculate, or you know what is the accretion rate, you can calculate what is the mass loss rate. So the points are results from numerical simulations for different cases. But the solid line, surprisingly, is the very old result by Castor Albert and Klein from the 70s. That in the high luminosity limit, the mass loss rate scales with the luminosity, or gamma here is the Eddington fraction, as 1 over gamma, alpha. Alpha is about 0.6. And this parameter alpha represents the relative contribution of optically thin lines to the overall opacity provided by optically thin lines. Okay? So this is all from the theory, well developed and tested against observations for OB stars and then wind stars. Okay? So when you have line opacity due to lines, you can have a wind for highly sub-Eddington source, less than 1%. But there is a limit to that. It's because if the luminosity is below the total opacity, sorry, 1 over the total opacity from all the lines, if they were optically thin, then there is no wind. In other words, the limit for having a line-driven wind is when this times gamma is larger than 1. If it's less than 1, even the boost from the lines is not enough for radiation pressure to overcome that. So it is good to know that this very old result, this old scaling, applies also, developed for spherically symmetric winds, applies also to axisymmetric systems like winds from disks. So people have used this, in particular Jerry Ostraka and his student Anna Choi and our current postdoc Amit Kashi in the cosmological simulations, where they have physically and observationally supported model for scaling mass accretion rate with the luminosity of a given system in the wind. Okay? So they can put this in here. They can measure the mass supply rate, assume that most of it or all of it gets to the black hole. That gives them luminosity, and they can now estimate what would be the mechanical energy released by this system. This is in context of very complicated calculations, right? So gadget 3 includes all these things. And Amit Kashi made this graph for me on my request to show how complicated the patterns are, how they are connected. So my talk so far focus on this, on understanding one feedback mechanism in this box, which is referred to as AG. And it's not engineered, as I tried to convince. So what we know of quasars because they are great sources of radiation. So what will happen to the gas which wants to be part of AGN? So gas which is on parsec or kiloparsec. When it sees this radiation, it will be photoionized, right? And it goes back to the 70s, where there was work by Jerry Ostraka and on one hand, and then Bisnafari on the other, when they talk about preheating and the fact that when you have a Bondi type of accretion and you heat up the gas will heat up, and you can find a situation that it will not be bound to the system, it will start to move up. And they had a debate about what is the maximum luminosity for which you can have a steady accretion. Okay? And Julian Krolik contributed to this debate by considering effects of thermal instability on this problem. Because if you have a gas which is heated up and it's photoionized and contaminated, it is known since the 60s, Eugene Parker and George Fields came with specific criteria for the gas to be thermally unstable. So this gas is not only heated up, but can be thermally unstable. So what happens to Bondi-like solution when the gas is heated up? Okay. So you solve the same equations, and for now you can just have heating and cooling. So what can you have for relatively low luminosity? Well, this is temperature as a function of so-called photoionization parameter. Remember that the optic in plasma, which is photoionized and components heated and conventional cooling, the temperature is a function of so-called photoionization parameter, which is the ratio of the flux and the density of the gas. So it's not the function of the flux separate from density. It's the ratio that matters. And this curve gives you the solution for the radiative equilibrium. Over here, temperature is so-called the Compton temperature, a quarter of X-ray temperature, and it's independent of photoionization parameter. Over here, you have dominance of line cooling and photoionization. Here, you have effects of Bremsstrahlung. And this region is known to be very unstable. the way to see it in this context, but it's consistent with the classical story, is that if you are over here and you perturb the gas under the condition that is of constant density, if you increase temperature, you will be in the heating part, so the temperature will animate and increase further. If you reduce temperature, then it will not catastrophically fall and end up on the lower.
Given the radiation to gas pressure ratio, isn't there a dynamical instability here as well?
Yes, but I made this for a low luminosity case where that contribution would be tiny on the imagery. So I would consider those cases later on, but for now let's just forget about the effects of dynamical radiation pressure, just on the photonization.
What's the specific ratio of X-rays to UV here? Does it matter much?
This just basically is, does not matter in the photonization parameter. It's just in the definition of photonization, you care only about the radiation above a certain energy. So it's the flux divided, but it's this number is proportional to flux divided by number.
But you also have this high energy tail that you move temperature depends then on the X-ray forms, right?
Yes, so here the yes. So the X-ray temperature was 10 Kelvin. So formally speaking, when you look at George Field's paper, you have a dispersion relation, and note that if there was no heating and cooling, you will end up with just the acoustic mode. And if you have this, you can have part due to either for isobaric and isobaric components. So you want to know what happens to the gas, which is formally subject to thermal instability. Kind of related to your question. So the way we studied this problem is we choose a very small X-ray luminosity, much less than the Eddington, 1% of Eddington. So we can forget about the force. And not surprisingly, we find a steady state solution. We increase the luminosity just a little bit, we find a steady state solution. Sorry. And also of the same mass accretion rate, simply because the amount of heating, the difference between and here is so small that the sonic point is basically at the same location. So the critical point is unchanged. And you can go even to 1% and it's still steady. And Maxwell's accretion rate is more or less the same. But when you go a little bit higher, you start to have problems with finding a steady state solution.
So is this cold accretion now? Are you effectively having cold blobs raining down?
Yes. I'll show you the movie.
Looks just like.
I argue that this is what happens in clusters.
Yes.
No, it's exactly.
That's right. Yeah, that's right. So I showed you the dispersion relationship from George Fields, but to study those mathematically and formally, you should be looking at the formulation of the problem developed by Stephen Baldus and Soccer and applied by others also to cooling flow and cluster problems.
Well, there's details about Baldus and servers. We'll talk about that line, but it makes some assumptions.
So here's an example of the of the flow structure. This is the temperature. So you mentioned about the temperature. So at large distances, say 200 parsec away, we start with the temperature which is with the gas which is in thermal equilibrium and has a temperature of say 40,000 K. And then the temperature goes up and reaches 10 million kelvins at the inner radius of the computation. And here's the Mach number, and 1 is over here. So the gas becomes supersonic at a relatively large rate.
This is after a long time, setting into a quasi-steady state.
It is a perfectly steady state after, say, 1 million years.
Oh, so this is still the one where it's stable after a long
That's
time.
right.
It's not yet the one where you...
That's this, yes. That's
This
right.
is multi-dimensional.
This is 1D. For now, it's 1D. We just want to understand the thermodynamics of the steady state solution and see whether it is stable or unstable.
And that behavior of the Mach number comes from the fact that if you looked at the temperature density relation, its temperature is increasing with less rapidly than what are the two?
I will show you an example in a book.
So sorry, what are the two curves in the top plot?
Or what's the scale for the Mach number?
Oh, so this is, I think this is 1, 2, 1, 2, 3, 4, 5, 6.
Well, what are the two curves there?
So
Red is the Mach.
black is temperature,
Temperature, okay.
red is Mach number. And then other things. So what happens? So these are contribution to the total heating and cooling from Bremsstrahlung. So Bremsstrahlung cooling dominates at smaller radii. Then you have photonization heating, which dominates heating at large radii. At large radii, photonization heating is almost balanced by line cooling, and constant heating is of little significance. And the net heating and cooling is shown here. And this is basically an indication when the solid line is, that means that the N in the dispersion relationship corresponds to unstable mode. So from here to there, the flow is formally unstable, and from here to here. What we also, it's heated up here and cools over here. Now, you mentioned dynamical effects due to radiation pressure, but there is also a balance between gravity and pressure, so you may have buoyancy. And we see this here, that where the regions are heated up, entropy is decreasing with increasing radius. So this is formally also unstable for convection. So what will happen when you increase luminosity by the sonic point between here and here jumps from over here to here. And now all this region where you have heating and cooling and which is firmly unstable now is in the subsonic part of the flow, meaning that those modes which are unstable will have enough time to grow while the flow is subsonic and stays in these regions for extended period of time.
So you get a gain region.
Exactly. Now, so what we did, we have the steady state 1D simulations, and then we put them on a two-dimensional axisymmetric mesh and repeated these calculations in 2D, where the initial conditions were taken from here, and we gently perturbed randomly the solution. And this is what you will see. And so the analysis of these calculations was quite time-consuming because we wanted to make sure what's going on. So this is time scale for this is dynamical time scale. This is for isobaric thermal mode. So this is thermally unstable, and it's much shorter than dynamical time scale here. And this shows that the isochoric and acoustic modes are stable. Acoustic modes are dominant. This is the curve which basically shows the square root of Brandtl mode. So this is where it is convectively unstable. This is convectively stable. So remember in Balbo's paper for a flow where the radiation is not position dependent, you can show formally that thermally unstable zone totally overlaps with convectively unstable.
So you mentioned a very important point there, that heating has to be a state function, a function only of density and temperature for this relation to hold. If
That's
you
right.
relax it and allow it to be a function
That's
of
right.
position,
For certain
this
conditions.
bolus and Soka result completely vanishes.
That's right. And in our case, you see that we have this correspondence that it's unstable convectively and thermally, but we also have regions where it is unstable for thermal instability, but convectively stable.
Okay.
Yeah? So with this knowledge of what to expect, we took this and put it on the grid. I will just skip that part and show you the movie, which will take a while. So this is run for quite a long time, and those perturbations first grew linearly and then non-linearly, and then the contrasts are quite high, 10, the factor of 10 or 100. But these perturbations were introduced only once. So it's possible that the flow can undergo this type of evolution and at some point will turn back to the original time-independent steady solution. And we have cases that happens, but this is a case where this did not happen simply because after initial thermally unstable phase of evolution, you have a phase when buoyancy dominates. You have this hot gas that starts to rise up and affects the flow in such a way that it will never return to a steady state.
But is this a function of the feedback, right? So is the radiation flux self-consistently determined by, related to the input?
Not in these calculations, because we want to have a full control, so we don't want to have too many variables. So the X-ray flux was fixed. The assumption is that this evolution is take place over a relatively short period of time, short in comparison that it would take for the gas, which is already sitting here, to be totally consumed.
Where is the sonic point in the initial state?
So for this location, sorry, for this parameter, it is about 1 to 4 times 10 to the 19.
But in that simulation,
Yes, so
where would it be? Why is it? Okay. 4 times 10 to 19, sorry.
so this is 19.
No, it's 10 to 20.
Sorry, over here.
Yeah. Oh, it's in there, right.
So you have a huge region where the thermal instability can grow under subsonic, in the subsonic part of the flow. And it can spend there a long time, so that the amplification can be quite high, like 10 or even 15 orders of magnitude.
So,
That's why numerically it is hard to obtain a steady state, because you are basically amplifying the numerical noise which is in any type of
I bet this is tough to converge, right? Because when we did some thermal instability calculations, we found you actually had to resolve the field length in the cold phase as well, which is incredibly challenging.
Yes.
So we had to cheat and change the temperature.
You had also, sorry to the question.
well, so the thermal stability is occurring near the outer part of the domain? Here?
Initially.
Initially. But your ingoing perturbations seem to change their structure, not the angular structure, the radial structure. Why is that?
The stretching,
Yeah.
so the gas is accelerating.
But, so you're adding the perturbations in its initial state, and some of the gas is sitting at a very large radius, and that stretching represents
The differential acceleration.
differential acceleration.
Yes.
But for the gas that's starting at the largest radius, where you stop, is there any significant change in its structure when it enters the domain relative to the gas that was initially entering?
It's got no perturbation on it. Right, you just got a smooth inflow boundary.
That's right. So
It looks like the nature of the perturbations
the
is
outer
changing.
boundary conditions when the gas was entering was unperturbed. It was smooth. That in some cases see that the flow recovers to the steady state, where the convection does not play a role. Now, it is not by design. It just happened. Is that when you look at this movie closely, you see gas which could be referred to as a hitchhiking gas. These are those bullets here, those clouds, which basically are cold. If not for the hot gas around them, which is flowing out, they would sink in, but they flow. So these are those regions here. So basically,
So they're ram pressure supported.
that's right. They fragment the cold filaments, and if they are light enough, they can be carried out by the hot gas that flows out. So this is the density, this is the temperature, and here's the velocity magnitude with the velocity direction.
So I just tried to do that in my head, but I got 10 to the 7 solar masses, massive hot gas in that domain roughly. Check that.
Oh no, the mass,
It was 10 minus 22. Did I
no,
just get it wrong?
even lower, 24.
Oh, the sort of orangey stuff is kind of like so,
In a realistic situation, how rotational would this gas be?
rotation. I will show you the cases of it. So this is the simple, okay, so in summary, I'm showing you this results of one of the most simplest setups you can think of. You start with a purely radial, time-independent, yet thermally unstable solution, and it evolves in nonlinear regime into this very complicated. So we have seen these things also in our SPH. So those simulations were done with zeros, so grid-based code. We've seen similar behavior in SPH calculations done by parameter where we see this cold accretion and hot accretion. And by the way, when we measure, we never found that cold accretion would dominate by a factor larger than 4 over hot. So some cosmological simulations, people find a need for cold accretion to be supernova. Right?
So you're saying it's 4 times higher than the hot?
The most.
At the most. But
At
it's
the
typically
most.
of order.
Yeah.
But,
Yeah.
so what about Ian's question about resolution and the difficulty of seeing the interfaces between the hot and cold?
So in 1D, we managed to, so these simulations were done with 512 points in radio. In 1D, Monica ran simulations with 4 times more grid points. And she basically measured the growth rate and tried to compare. And we found that you need to resolve the fastest growing mode by, I think, at least 8 grid points to get the growth rate the same as predicted by the spectral relationship. In 2D, it would be very hard to do that. So we encountered the very same problem.
It seems like that's the linear rate, whereas the nonlinear evolution also has its own problems.
That's right. That's right. So what will happen when you change the radiation field geometry? Instead of a point source, you will have a disk before you add rotation. So that's another question. So now you have a situation where this radiation comes from the disk. So there's a cosine dependence. There's more radiation flux here at the given location than here. That corresponds to the fact that, and then you have radiation pressure. This is for high Ellington fractions. That you can allow for an inflow here, but you will have an outflow over here. And that would be a function of spectral energy distribution, something that you mentioned. Over here, I have X-ray contribution and UV contribution. Just happen to assume that they are 50-50. What will happen if I change that and make it more like in quasars, where mostly it's UV, very little in X-rays? Looks like that, mostly inflow. Except that there's a very narrow region where there's a very powerful outflow. So what happened by changing this number is that you don't heat the gas so much. So the gas which is exposed a lot to UV will be cooler, surrounded by hot gas, so it will be compressed. But in this type of calculations, you can directly address the issue of the feedback. So how much gets out for a given amount that gets in. So in this very narrow outflow, I found that the outflow is quite powerful, so that only 10% of what originally started as an inflow reaches the inner radius of the computation.
What are the units of R?
So this corresponds to 7 parsecs.
7?
Yes. So this is in units of the black hole radius. So this is for historical reasons. Now, so there's we can also measure how much energy is carried out by this outflow in kinetic and thermal form. So since this gas is cold, the outflow brings very little thermal energy out, but it's quite powerful. And then, yes.
You say that only 10% of the inflowing gas actually reaches the inner edge. Isn't that in conflict?
Yes, that's right.
Isn't that in conflict with your statement that the ring is driven from small radius? If gases and
So
everything.
this is the profile. So initially there is but this, the statement was for the disk winds. Now these are winds from inflows. So this is the gas which basically was falling in and turned around and became an outflow. So when you follow inflow rate, you see it's initially radius independent. But then as we go to smaller and smaller distances, we see this number goes down because there is an outflow. So when you add those two, subtract those two numbers together, you get the net. And you see it's steady state and flat. And the 10% is the ratio between this number, sorry, the number over here to the number over here. So this type of winds are good in turning around huge amounts of material and pushing them outwards. They are not very energetic. So adding rotation, what you basically do, you add centrifugal barrier to the problem. That the gas which is accreting cannot get very close to the rotational axis because the centrifugal force will not allow it. So this gas will converge here and it will be blown away and fragment due to the dependence of radiation pressure on density. So certain parts will be experiencing stronger force than the others, and that will cause the outflow to. Yes.
How the rotation of the central object would affect those parts?
You mean of the black hole?
Yes.
Well, it would, if the black hole is spinning, so for a given amount of accretion, it would be brighter. But we are not concerned with this. So for us, the luminosity of the central object is just a number we assume and keep fixed. For now, I will change that later. And then you add you can add X-ray background radiation, and you can see that things become very complicated when you have not only thermally unstable gas, buoyantly unstable, but also rotation and X-ray heat.
So what do you mean by X-ray background?
Excuse me?
What do you mean by X-ray background?
Oh, over here is, so I have two components for the X-ray. One is coming from the point source at the origin, and the other is just a position-independent X-ray.
Like some X-ray halo.
That's right. I just did it because, as you can see, resolving those huge density contrasts was a nightmare, so I wanted to see what will happen if we don't heat it up. So this is fairly old stuff. So it looks like that, and this is the cheesy part of my talk. So it looks like this, you see. So do we have a model for dynamical clouds, a dynamical model for clouds, right? So this is like that. This is the standard, this is the unified unification model. So I think the agreement is quite good, and there's still a lot of work to be done, but some of it is easy. You can improve this model by just turning it a little bit. Right. So we have something that the answer to the problem of survival of clouds is this. No, those clouds are being destroyed very quickly, as predicted by many before. But we see that they form quite efficiently. So you can have always a generation of new clouds when you have rotation, thermal instability, and those effects which are naturally to be expected in systems like that. But there's a problem. Over here we have a lot of inflow. When you take observations of AGN, you see mostly outflow. So is this model consistent with observations from this point? So before we attack this, this was all axis symmetric. So Ruichi Kurosawa basically rerun some of our 2D calculations in fully 3D. So as the previous slide was kind of cheesy, this one is actually very nice movie, where you see the flow which comes in. This is centrifugal barrier. Here, just turn around, and it's a rotating flow. So you see that those clouds are not rings, but they are actually individual clouds.
What's the scale? Where's the gravitational rate? Is that way in?
So the scale over here, outer radius is 7 parsecs, which is about, I think, 2 or 3 times the Bondi radius for the corresponding state.
But you've got the inflow's all hot there because you don't see any, or at least.
That's right. So what we did is we called Stewart and we asked him to use his machines to compute spectra for now different inclination angles, different phi angles, and different times. Okay? One of the things is that in 2D, clouds are less dense than in corresponding 3D because you have one extra dimension to compress. And since cooling is the density squared, you can expect significant differences between 2D calculations and 3D calculation in terms of the density structure and spectra. So depending on the angle, so this is the cosine of theta, you have places where do not see any too many spectral lengths. It's because the inflowing gas is hot, fully ionized, so there are no spectra. And then over here we see for a given inclination angle, so looking down the most interesting part, you have normalized flux, net, and then the scattered part, and this is the transmitted part. And this is to have connection with observations. You can see that there are many interesting spectral lines, and one can now try to compare models, the predictions of these models with real observations.
So there's no cold disk in the picture here at all.
The cold, in these simulations, the cold disk is only implicitly as the source of radiation.
Well, but I mean, out of
You know,
parsec.
the incoming stuff hitting the centrifugal barrier.
By design, learning from our experience where I calculated formation of the torus from rotating gas, by design, when I added rotation, I made it very small so that circularization radius was smaller than the inner radius of my computation domain. Because what will happen if I would use slightly higher rotation rate, I would start to see formation of the torus over here, and that would affect calculations and slow down them. So this was just a preliminary stuff. So I, by design, made all this converging inside. So in 2003, I did something similar. Now, some of you, I think, Ian, asked about the feedback. Coupling now, remember my very first slide was one of the first slides where you take the accretion rate, measure the accretion rate, calculate luminosity based on it, okay? So now, which you repeated this calculation where we are now measure the inflow rate of the inner boundary and use it as a proxy for accretion rate onto a black hole and use 10% efficiency to calculate the luminosity. So now for a given density at the outer radius, we can have self-consistent accretion rate and corresponding luminosity of the source. And by changing density, or increasing density specifically, you can increase accretion rate, and you can measure what will happen with the outflow rate in a self-consistent manner. So initially, when the density is low and mass accretion rate is low, you see that the higher the density, the higher the luminosity, and the higher the outflow rate. So this is this part. But as you go to higher and higher densities that correspond to higher and higher luminosities, you see saturation. That despite the system going, emitting more radiation, you don't have stronger outflow. The reason for that is in the geometry. When you increase luminosity, you basically increase the solid angle occupied by the outflow. So because so you basically turn more and more of the inflow into an outflow. However, there is a limit to that, which is 90 degrees. So when the luminosity is very high, you basically turn outflow from wherever, everywhere except for a very narrow wedge around the equator. So the inflow is over here, and it's not subject of irradiation because it's high column density. So it is not, it is only heated on the surface, and the outflow is over there. And now you see that you have a huge region where radiation escapes without encountering any wind, any gas. So as far as launching a wind, in this part radiation is wasted. So that corresponds to the saturation. And by the way, because of that, we don't see that the luminosity or radiation from the black hole on these large scales, remember parsec scales, regulates the inflow rate in such a way that it will prevent inflow rate to be smaller, from being larger than Eddington limit. So there must be some other mechanism that will take care of that problem. So you cannot count on outflow from parsec scale in regulating the inflow rate so that it will not exceed formally the Eddington limit.
But the bottom line here is that there isn't a self-consistent calculation of the mass flow reaching the black hole and actually generating those photons.
That's right. And we added some delay, so it is not because the lag that we added basically our accretion inner radius is say I think 1500 black hole radii. So we account for the fact that at a given time that the accretion that the gas which is crossing inner radius at a given time will reach the black hole dynamical time times some factor of 100 corresponding to the viscous time scale. So it's not an instantaneous coupling, it's with a delay.
I was just trying to put in my head, work through how this would scale the black hole mass. Because if you imagine that the luminosity coming out is proportional to the mass, the sun, then for a given soundscape of infinity, the radiation flux at the Bondi radius would go like 1 over the mass. Because Bondi radius goes
That's right. So we can think about it as that the temperature at large could be say.
But the Bondi radius is basically, Bondi temperature is basically, until you start heating upstream of the original sonic point, it's basically fixed by the conditions of infinity.
Right. Yes, well, when you start to explore things for different black hole masses, another complication is the spectral energy distribution. So it's worth exploring that. We haven't done it yet. So this self-regulation works to some extent. And going back to this business of hot and cold, so there is a total feedback energy. What we find here is something which I mentioned earlier, that you can turn a lot of material, but in terms of energy, this is very small. So this number is hard to read, so I wrote it again using larger fonts, that it is 10 to minus 4. So in most cosmological simulations, people require things at the level of 1%. So that's probably not the region or the mechanism to do what cosmological simulations require. So in summary, in AGN feedback galaxies calculations, you have huge range of distances, and you have a whole list of processes: AGN wind, young stars, supernovae, AGN X-rays, supernovae of different type. So I talked about two: AGN wind and X-ray. And the question is, what does it do and where? Okay. The answer is, when we look at the calculations that look at it, is that AGN wind probably is responsible for heating in falling gas and limiting black hole growth. So that's the part 1 of black hole. And it operates on those scales. So up to maybe 1 kilopascal. This part is probably responsible for heating the cooling flow and driving galactic winds or outbursts.
Galactic winds in the hot gas.
Yeah, that's right. So you saw a lot of clouds. So let me finish very quickly by showing preliminary results from the project that I mentioned earlier.
I would cut you off, but I'm going to let you show this.
So I was not solving those equations. I eliminated quite a bit. But with shade, we actually can solve all of them, and we did. So imagine that there is radiation coming off here, and there is this cloud, and it is with a relatively low density contrast. So that's what happens to this optically. Radiation goes through it very quickly, hits the gas almost everywhere, and it expands like a balloon and disappears in the ether, back here. So there's no, there's just behaving like that. But increasing the contrast by a factor of 8 makes the cloud optically thick. Now it loses material on this side, and so it's evaporating on this side. It is compressed, and then it starts to move due to the well-known recognized mechanism, which is referred to as a rocket effect by Ort and Spitzer in the paper from 1954.
Don't forget fertility.
Excuse me?
Yeah. There was a phase that it looked like you were going to look like a fertility in the case solution, but now it doesn't look like it.
Spark symmetry.
So the acceleration
We
is mainly
should-
by the backflow.
Yeah,
the
rocket,
rocket.
that's right.
Okay.
So this is purely absorption case. You can consider now scattering effects and radiation pressure being more important.
So ultimately, one is interested in structures that could survive, because that looks very transient, right?
Right.
So what role does self-gravity play in all this?
Self-gravity?
Yeah. If you have especially if you have a very hot confining medium, and there's a big temperature contrast, you might think it's
We ask after it because I think other people. We'll let Andrew.
So I'm done. Sorry for taking that.
One of my questions.
I owe some of you to give an update on the discrete stuff. There is only a lot in the inside. So, as far as AGM feedback and energy, I think that discretes are much more promising than anything else. They move very fast. They carry a lot of material, which is nothing new. AGM winds have been blamed for many things, including increasing the velocity throughout the galaxy and beyond.